Report to cloud. Good. Good afternoon, everybody. Welcome to the IFT Monday seminar. And I'm very happy that finally we could get Pier Paolo to talk about his work. Pier Paolo was postdoc at the IFT until end of September and now moved to Santiago. And yeah, it's a pity that we couldn't get it while he was postdoc, but I'm very happy that it works out now. And please, Pier Paolo, tell us about your recent work.
Thank you very much. Thank you for the invitation. It would have been nicer to give the talk, of course, in Madrid, or at least to come back to Madrid to give the talk. Unfortunately, well, the situation is what it is, so there's not much that we can do. So I will talk about how indirect searches can be used at LHC and Collider in general to look for new physics, and in particular how effective field theories are a very useful tool and can be used to further understand and interpret what indirect searches are giving us, what precision measurement giving us. So let me start well, remind you something that you already well know, that with the discovery of the Higgs, now nearly 10 years ago, actually, we finally have a good picture of how nature works up to the TV scale. So we finally have a better understanding of all the characteristics of physics, well, many characteristics of physics up to the TV scale. However, that unfortunately leave us with 16 order of magnitudes of energy that we still have not really, we have still not explored. And most importantly, it leaves us with a number of questions that still lack a proper answer. Some of these are more theoretical in nature, like the correct description of quantum gravity, how and if and how forces unify, and not if not, why not? Because their couplings are very similar. And maybe one of the most famous one, at least for people who works in phenomenology, is the hierarchy problem. So why there's such a difference between the fundamental scale of quantum gravity and the fundamental scale of the electroweak theory. There are many more questions in more phenomenological nature, like what gives a mass to the neutrinos, what's the nature of dark matter, why don't we see, where is all the antimatter, why don't we see more antimatter, and so on. These are a lot of questions that we still have no answer. Now, the real problem is that not only we don't have answer to this question, but we really don't have either, we don't really know where to look for answers, in the sense that in this huge landscape that we have still to study, we still to discover, we still don't know where the new physics will appear, and where answer to this question could be found. However, it's reasonable to try to look around the TV scale, mostly because some of these questions have natural, let's say, natural answers around the electroweak scale, and at least one of them, the hierarchy problem, involves the electroweak scale by itself. So we don't know where to start, but at least the TV scale seems a good starting point. So now the question, how can we look for new physics? And in particular, how can we look for new physics at colliders, at LHC and future collider? There are mainly two paths that one can try. Option one, I call it, but we'll go in more detail later. But option one is the direct search. Simply look for any bumps, any missing energy, any direct sign of some new state that shouldn't be there according to the standard model. Option 2 instead is a more indirect route, and it regards the study of modifications of the standard model processes and relations, and the precise studies of this process in the relation, and so that any modification that we can find could be in principle due to some new physics interactions. So that's a more indirect search, of course. Now the two options. So let me give you an idea of what are the positive and negative of the two options. Of course, when I say about the two options, it doesn't mean that they are necessarily mutually exclusive. You should actually go for both of them and try in any possible direction. Of course, that's a given. However, it's also true that some accelerator, some machine is better for one kind of search and others for other. For example, E+ E- machines are usually better at precision physics simply because you have a much better control of initial state since you have just electron and positron. And so you can have much more precise measurements of your final states. On the other hand, hadron colliders are usually better at reaching higher energies. So that also means higher luminosities, and so in general, they are better at discovery. That, of course, doesn't mean that you cannot do precision physics at hadron colliders or discover electron-positron machines. But this is just a general attitude, let's say, of the different machines. So now, direct searches are definitely a necessity for discovery. There is no way to say that we discovered new physics without actually finding a bump somewhere in our spectrum. As an example, old example, but as an example, we knew that the W was there around since the Fermi time, but we couldn't say we discovered the W until the 80s. However, in general, direct searches are heavily model dependent, meaning that you really need to have a well-defined model to start from in order to actually discover something. Any experimentalist will tell you that they will not look for exotic channels if they don't have a good reason to look for them, a good model to look for them. So in this sense, they are more limited, or at least they are more difficult. You need to have a good idea of what you're looking for before finding it what you're looking for. Indirect searches, on the other hand, are virtually model independent. Say virtually because, of course, there's always some small dependence that you can introduce. But in general, you can have assumption, or you can get result on your physics without making any large assumption, apart from knowing that the standard model is a good theory up to the TV scale. So your only assumption is that the way you're picturing physics up to a certain scale is correct. On the other hand, they are more difficult to interpret. You may see just a modification of a scattering, and you don't necessarily know what that means, if that's a new state, if it's a bosonic or fermionic or whatever, or what would be necessarily a scale. So this is the situation. Now, while direct searches, as I said, are necessary for discovery, indirect searches can cast a wider net, and they can help us steer our research in the right direction. So this is the main point. Now, right now, LHC has run a lot of direct searches in a lot of different channels. This is the result from Atlas Exotic Searches of May of this year. And there are many different channels that have been explored, and for now there are not been any new physics appearing. So for now, the direct channel direct route that didn't give us what we hoped for. So in this talk, I will instead talk about option 2. So going a little bit more in detail on option 2. Not only talking about indirect searches, but also how to use other theoretical tools, EFT, to systematically look for new physics using indirect searches. So this is the plan of the talk, let's say. So before going on, let me give you an example of what I mean when I say that indirect searches can help us cast a wider net. So let me introduce you the electroweak precision observables that I'm sure all of you know very well. The mass of the W and the Z, and the electroweak mixing angle, the Fermi constant, that, as you know, is connected to the decay of the muon, and the vacuum expectation value of the Higgs, and the fine structure constant. Incidentally, these few observables are also the most well-known, most precisely measured quantities that we have in particle physics. And the good thing about them is that there are a certain number of relations that put them together, so you can write a certain number of relations between all of these objects. Some of the relations are easy to write down, others are more convoluted. But the main point in any case is that if you can measure precisely one of these quantities or one of these others, you can find inconsistencies in the equality. You can look for inconsistencies, and that would be in principle a sign, could be in principle a sign of new physics. Now, in general, these relations are modified by perturbative corrections, by loop corrections. So that unfortunately introduces dependencies on other inputs that are not so well measured, like the mass of the top, or well, even not well defined actually, like the mass of the top, the strong coupling, and the mass of the Higgs also. So you have also these other inputs that unfortunately make this equivalence less precise, or known less precisely. Sorry, but in any case, if you just go on face value and use these relations with all the quantum corrections, what you actually obtain right now is that there is a small inconsistency without the mass of the between the mass of the W. Between the measured mass of the W and the predicted mass of the W. You can see that in this plot by G-Fitter. The green bands are the direct measurements for the mass of the W and effective sign, and the blue blob is the result of the fit of the fit on the other parameters. So as you can see, there is this small about 2 sigmas inconsistency between the two. Now, of course, a 2 sigma uncertainty, considered inconsistency, is not a proof of new physics, unfortunately, because otherwise it would already be claimed. And most probably it will go away once new measurements or more precise measurements or more precise theoretical calculation will come along. However, it's in any case fun to try to imagine what kind of new physics would generate such a difference in the mass of the W. Now we don't have much to go on. We just have one single point, that is the mass of the W, and maybe we can assume that the couplings are perturbative just to avoid to introduce a new strong sector. what happens is that if you just plug this in, you basically have only a couple of possibilities, either something that is charged under SU2 and that has to live somewhere much above the 1 TeV scale, possibly fermion, or something that is not charged under SU2, possibly a scalar that that lives around 1 TeV and connects only to Higgs or other fermions. So this is admittedly, this is not telling us a lot. This is not a lot of information. In fact, in general, you can use this. It's more useful to eliminate theory rather than, or at least to constrain theories rather than model building. However, it's still a starting point in a sense, and it gives you the idea of what I was. I hope it gives you the idea of what I was trying to convince you, that you can have a wider look at any possible new physics. Also, as I was saying, this is only 1 point. It's only the mass of the W. So you can extend the search and include the whole list of precision observables. These objects have been given to us mostly by LEP. The most precise measurements are still by LEP, and apart from the one that I introduced before, include the width of the W and Z, the different various kind of left, right, and forward backward asymmetries, and ratio between decay width and cross sections. So all these objects all together can give us a better understanding of what kind of new physics could appear. But now we arrive at a second problem, and the second problem is that we have too many objects and too many possibilities, too many interactions that are changing altogether. So we need something a little bit, some instrument, some tool to try to make a sense of all this list of numbers. So historically, I'm sure that you know them, but historically, tools that have been used are the famous STU Peskin-Takeuchi parameters. These objects are related to the corrections to the vector boson propagator, so the little loop here on the left. And they're sensitive to different kind of new physics. However, like for example, new Carré fermions or physics that breaks the custodial symmetry. However, this is of course not enough to investigate a more general new physics. And this you can actually understand it a little better if you consider that at the very end, these SN2 parameters are directly related to the correction to the mass of the W and effective sign. So at the end, they don't really give us much more information than those two parameters. And we already saw that we have many more that we have to work around. So we need something a little more general. Now, a more general way to do that, it would be just to consider, take the standard model couplings and consider small modifications of these couplings. This is the so-called kappa framework, because what you actually do is to multiply your standard model coupling by a kappa. And then when kappa, for very small kappa, give us information on high energy scale. This has been used a lot in the Higgs sector, is still being used to explore the Higgs sector. Here on the left, you have a list, well, you have the result from 80 inverse femtobarns, so not too far away. From Atlas, so I studied from Atlas, and well, apart from the fact that you can see that it's basically standard model, you can see that, yes, it's still very, very used and well understood and well used. Now, the problem is that the kappa framework as it is not a well-defined quantum field theory. Most of all, is not gauge invariant. So that makes it makes impossible to do, for example, loop computation in this theory, because that would blown up. And while you can use it at tree level, the leading order to investigate modification in the Higgs sector, they would wreak havoc in any study that you want to do of the electroweak sector. So you have to use something a little smarter. So we finally arrived to the effective field theories. So I'm not going to introduce you what an effective field theory is. I suppose everyone knows. But I'm going to introduce you to a standard model EFT. That is simply the idea that the standard model is not a UV theory. It's a low energy limit of some effective field theory. Now, this effective field theory is built in this way. You take the Lagrangian of a standard model, and then you simply add a tower of all the possible operators. These operators are defined as a certain scale lambda that is defined as a scale of new physics. So the scale after which you would start sensing new physics. And all these operators are built so that they respect the standard model gauge symmetries. So these are the main ingredients. Of course, there are some assumptions, so it's not completely free of some assumption. One is that there are no light particles. There are no particles below scale lambda. This is, of course, a little bit restrictive, but not too bad, because we already saw that for now there are no signal of new physics below, let's say, 1 TeV. So if this lambda is 1 TeV, it shouldn't be okay. On the other hand, the second assumption is the Higgs is part of an SU2 doublet. This is a quite restrictive assumption, because you can, in general, could in general take the Higgs to be the Goldstone boson of some new theory, and so have a more general approach. We'll come back to this at the very end of the talk, just for a second. So for now, let's run with this. Now, the theory, the good thing about this theory is that now it is renormalizable order by order in lambda. And I will come back to this later to explain this point and its importance. So let's give a look at the standard model EFT. Now, first of all, we have the operators dimension 5, and there is only one. And this one is the Weinberg operator that anyone that works in with the Majorana neutrinos recognize as the operators that give masses to the neutrinos. So this is there. For the rest of the talk, I will just ignore it, or in any case, put it to 0. So, but of course, you can reintroduce it. Now, dimension 6 operators are a bit more interesting, at least for what I'm going to do. And they have been categorized in this paper in 2010. And their full list is given here on the left. You can see them very small, sorry, but it's there, I promise. And there are 56 linear independent operators. These 56 linear independent operators have a total of 76, let's say, flavor blind or flavor diagonal coefficient. That means that you just not running on a flavor. You have a little bit more coefficients than operators, because some operators have a CP odd and a CP even part, so you split the coefficient in two. But when you consider the full dependence on the flavors, you actually run to 25,000 operator. Sorry, 2,500 operator. Yes, that would be. 2,500 operators. So this is one of the major problems of the standard model IFT, since, as you can see, even in the simplest scenario where you consider everything flavor blind and everything CP even, for example, you still have 56 coefficients that you have to fit in any fit. So that makes the study of this object extremely difficult from experimental point of view, but also very difficult from a theoretical point of view, since it becomes very arduous to interpret what all of this mess actually mean. So now, so this is one of the major problem of the standard model IFT. And let me dive a little deeper and concentrate again on the electroweak sector. So this is a list of the all and only operators that modify the electroweak sensitive observables that well, the electroweak observable. So these are the only one. And you can divide them in groups. This blue one are modify the couplings between the gauge bosons and the fermions, as you can see if you look at them. This red one is a modification of the definition of the Fermi constant. I remind you the Fermi constant is connected to the decay of the muon, meaning it's connected to the 4 fermion interaction of left currents, and is exactly what this operator is. This yellow one modify the triple gauge coupling, and it doesn't enter usually electroweak precision observable. So in general, at least for the rest of this talk, you can just not consider it, but I mean, it's there. Finally, these two green parameters are actually directly related, apart from coefficients, but they're directly related to the TNS Peskin-Takeuchi parameter. So this is actually a proof of what I was telling you before, that the Peskin-Takeuchi parameter are not enough to describe every possible new physics that appears that modify the electroweak precision observables. So now one can try then to, since we are restricted our vision only to the electroweak sector, so we are going just there, we can try to use the electroweak precision observable to bound only this. We put to 0 the trilinear, because the triple gauge coupling, because it's not interesting. So now, what is the Lagrangian, the effective Lagrangian for the electroweak precision observables? Well, it is this one. So this is the Lagrangian for Z and W boson, and how they would interact with fermions. And you have a new modification of some standard model couplings and new couplings entering in. Now, these 3 red ones are related to currents that are not in the standard model, like, for example, the coupling between the W and the right-hand currents. So for the rest, we can just ignore them, since they would enter only very high level in perturbation theory. So these other two, the coupling between the W and the left currents, are actually related to the coupling between Z and the other quarks due to the isospin SU2 symmetry. This is only true at leading orders, since when you go at higher orders, you break this symmetry. So in principle, you release them. But so for now, you only have this. So the only effective parameters that you have, the only new effective parameters that can change the electroweak precision observables are these 7. And together with the mass of the W, that gives us only 8 combinations of observables that can be probed at the same time. Wonderful, apart from the fact that if we go back, or well, I give you here the table. If we look at the operators that modify that Lagrangian and enters in the Lagrangian, you see that there are 10 of them. So that means that whatever fit you do using all electroweak precision observables and only the operators that modify the electroweak precision observables, you always end up with two flat directions. So in general, you don't end up with a meaningful fit, meaningful general fit. Okay, very well. So what can we do? Well, first of all, we can recognize that there is actually that restricting yourself to electroweak sector actually doesn't really make sense necessarily, because there are a lot of relations between different sectors. This beautiful picture from the HAPFIT collaboration gives us correlation in the measurements of effective couplings in electroweak, Higgs, and 3-gauge coupling measurements at current and future colliders. And you can see that all these measurements are related to them, to each other. So saying that you separate them is not necessarily meaningful. The other thing that you have to realize is that when you consider a perturbation theory, loop corrections actually make these connections between sectors even stronger. And to give you an example of this, let me step into a slightly different sector and go to the Higgs sector. So in particular, let me talk about the Higgs potential. It will make sense in a bit why I'm going here. So the Higgs potential is well known, and after the breaking, it has the usual shape that you know, where the coefficients of this potential are well known, because they are the mass of the Higgs that is well known, and the vacuum expectation value of the Higgs that is also well known. But of course, if you want to know if there's any new physics there, what we would need to go look for is if there is any modification of these couplings. For example, if there's any new interaction modify the Higgs trilinear coupling. So that means that we would like to measure this Higgs trilinear coupling. So how do we do it? Well, there are different ways. Sorry. So there are different ways to measure the Higgs trilinear coupling. First of all, we can try to extract it directly from double Higgs production. This is the standard way to do that. Now, this is, of course, all well and good, apart from the fact that the cross-section of this channel is extremely small, at least compared to the single Higgs final states. As you can see here in the box in the right angle. This is due to the fact that, apart from the fact that the Higgs, that you have a heavier final state because you have 2 Higgs instead of just 1, and you have an additional weak coupling because, well, you have now the trilinear. And there's also a destructive interference between the two amplitudes, the two diagrams that I show you there in the plot. The triangle and the box diagram interfere with each other, and that makes the cross-section very, very small. On top of that, the main channel to discovery would be the decay into four Bs, 4 bottoms. And that, of course, is very challenging in an hadron machine where the 4 bottoms channel is swamped by the whole QCD background that you have in a hadron colliders. So one can try to imagine other ways to measure this trilinear, and one way would be to realize that the trilinear actually enters in single Higgs processes. For example, here I give you the decay of the Higgs into vector bosons. And you can see the dot again is the trilinear, and you can see that it appears there. It also appears in all the other decay of the Higgs and all the production processes relevant for LHC. Now, in order to study trilinear in this way, it's convenient to go back to the kappa framework. This is so that is to modify the Higgs cubic term of the potential with a kappa that gives us an idea of where new physics could be. And okay, but okay. Sorry, I lost my words a second. Okay, so now there is also another way, though, and this is why I was relating that to the electroweak precision observables, because one can realize that actually also electroweak precision observables depend on the trilinear, this time at 2 loops. And while now we're talking about 2 loops object, so next to leading order corrections instead of next to leading order corrections, the fact that we know that electroweak precision observable so well gives us hope to try to find the Higgs trilinear through these processes. Now, before going on to the actual result of those methods, one of you may wonder, what does it mean to calculate corrections in a kappa framework? I already told you before that the kappa framework doesn't allow to do loop corrections, because you cannot use it to do anything else than leading order calculation. So in order to justify why we use it, let's start with the Higgs potential. So the VSM is the potential in the standard model that we replace with a new physics potential that is simply a towers of phi dagger 5 or Higgs squared terms in the Lagrangian. So instead of having only phi dagger 5 and phi dagger 5 squared as in the normal standard model, we build a whole tower of new operators. And then we expand these towers in general, and when we consider only the first terms up to 4 fields interactions. And this is the Lagrangian that you obtain, where psi here is simply a shorthand for Goldstone boson. So just consider phi is a 2-field object. Doesn't matter. What we notice is that there is a correlation between different modification of this potential. In particular, there is a correlation between the modification of the Higgs trilinear coupling, and that you see in the left part, and the coupling between 2 Higgses and 2 Goldstone boson in the right part. You also notice that the quartic coupling of the Higgs instead is something different, something that is not related to that trilinear coupling necessarily. So if we call now the term the term that is in front of the Higgs cubic part the trilinear, so we have the kappa lambda, we can see that in our if you do a calculation where the quartic doesn't contribute, your kappa framework actually is equivalent to the EFT. So just to make sure that everything is kosher, let's say, what I'm saying is that for us, for this calculation, the kappa is just a shorthand for effective field theory. It's just a way to try to understand effective field theory in a bit more smarter way than having an n tower of operators. But it's all effects is the same thing.
Excuse me, may I ask you something?
Yes, of course.
Are you working in a particular gauge? I mean, RG gauge, or because the interactions in general, they will depend on the choice of the gauge.
So the calculation, the result actually do not depend on the gauge. We did the calculations of all the interactions on the trilinear in a general gauge, and they not depend. This is because, as I was saying, there's a relation between the Goldstone bosons and the Higgs. So you can actually reintroduce the Goldstone boson in your calculation. You don't have to put them to 0 or anything like that. You can keep them and relate how the Goldstone boson interacts with the Higgs with the kappa of the trilinear. So that basically allows you to do a gauge invariant calculation. So to answer your question more briefly,
I will ask later, okay? Not to interrupt you.
Oh, okay. Sure. So going on. So these are the constraints that one obtain using this method. So here we have the constraints that are obtained for run 1 and run 2. These are the constraints that are obtained from directly the Higgs pair production. While these 3 are the one obtained using single Higgs production and electroweak where possible. So the run 1 result were made, we're calculating our paper, and we use there the result from the Atlas CMS combination of the time plus the PDG electroweak. While instead the result from run 1 have been done by the experimentalist and were presented at Morion last year. So these are not our result; they are done by the Atlas collaboration. So as you can see, the constraint that one obtains using the different methods are similar, and that means that in general you can imagine to combine them to have more stringent bounds. That combination has not been done yet. Actually, that combination is a work in progress, and what I can tell you is that even for a present result of the LHC and possibly future result, what you can expect is that electroweak precision observables together with single Higgs processes and double Higgs processes will give stricter bounds, can be combined and give stricter bounds than what you would obtain using only Higgs results. So this, I hope, clarifies a little bit when I say that there is this relation between different sectors become more and more strict and intercorrelated when considering higher loop. So now let's go back to the standard model IFT. As I was saying before, there is a definition of renormalization that allows to do loop calculations in the standard model IFT. This definition is operatively means to do your calculation, fix the power of lambda you're interested in, and throw away anything that carries higher powers of lambda. So to be a little more clear, let's consider this process to 2 Higgses into fermions. The coupling between 2 Higgses and 2 Ws is, of course, happens in the standard model, but also has a coefficient in the standard model IFT, in the IFT. While instead the interaction between the fermions and 2 Ws exists only in the EFT, at least written in this way, a direct interaction. So what you obtain at the end is that this diagram, it's proportional only to the coefficient C2, because every term that is of C1, C2 would simply thrown away. Now you may have noticed that this diagram here is actually a correction to the diagrams of 2 Higgses into fermions. So you can write, you can see that this object is a correction to the coefficient, to the EFT coefficient of this diagram. So in general, that means that this is a general statement, and it tells us that all these coefficients that you have, all loop correction to these coefficients, or can all involve other coefficients. This one says in general that the EFT coefficient mix, or if you want, they simply run or RG. So if you start with a set of operators, if you start with your leading order operators, when you renormalize, when you do loop corrections, you end up with a much larger set of operators. So this is also something that has to be taken in mind when considering this loop calculation in the EFT. Okay, so now armed with all the expertise we got until now, let's try to see what happens when we actually do a full calculation at next to leading order in the standard model EFT. As an example, I'll bring you again the mass of the W that we already know. So the delta R here are only standard model standard model corrections, and they're all known since, well, there are many results and new results. Includes 2, 3, even 4 loops calculation. So they're all there. But this other correction, the one that are completely EFT, instead are new, at least for the next leading order. So here you have, you have the two terms of this correction. So delta M W leading order is the result when you consider only leading order terms that enter. Next leading order instead is leading order plus the next leading order correction. So it's a full next leading order result. What you can notice is that, as I was promising before, talking about RGE, now you have many new operators that enter a next leading order. So you have many new objects that correlate information between different observables. You have also quite a bit large corrections to the coefficients. Correction that can be even 10 to 30% large. So you have all of this, and you can repeat this exercise all the time you want, and you can repeat it for all the electroweak precision observables. We did that, and we use them to try to understand what's happening what happens when you try to fit them to the using lab data. So we start with the whole set of electroweak precision observables. We do all the next leading order calculation. We did all the calculations, and then we decide to simply put the next leading order operators the operators appear only in next leading order to 0. That simplifies a lot the result. We then set the scale of the physics at lambda, and we fit on the data. So these are the results for the single parameter fit. Single parameter mean that we select a coefficient, we put all the other to 0, and then we fit on that coefficient. And we did that using leading order result and next leading order result. And here reproduced are the bounds that we obtain for these coefficients. We also consider a marginalized fit, where we fix, we take an operator, we minimize with respect to all the other operators, and then we fit over that over the original one. Again, we do this in leading order, next leading order, leading order, next leading order. Now, if you remember, as I said, there are flat directions, so we cannot fit on if we do a marginalized fit, we cannot fit on the whole set of operators. We can only fit on 8 of them or on 8 combination of them. So just for simplicity, we put to 0 2 of them that are the one that I give you there. Of course, the result of the fit will depend on which operators you are putting to 0. So now the result of our fit is presented here in this table, in this plot. Sorry. So these are the size of the bounds on the effective field theory coefficients obtained with a fit on lab using single and marginalized fit at leading and next leading order. So the first thing that you notice, and that's good, is that the single fit delivers stronger bounds than marginalized fit. This is just a proof that at least makes what we're doing make sense from mathematical point of view. The other thing that you may notice, is that the correction to the single fits, the next leading, sorry, the effects induced on the single fit by next leading order correction tend to have a negative sign, meaning they tend to give tighter bounds, while on the other hand, they tend to give looser bounds on the marginalized fit. This is quite an interesting result because it means that at least the sign of the effect of keeping next leading order, adding the next leading order corrections when you're doing the fit depends actually on the details of how you're doing your fit. This is a bit more clear if you let me define the size of a next leading order correction, that is defined as the next leading order bounds minus next leading order bounds normalized over leading order bounds, and the plot is given here. And you can see that the yellow bands that are the single fit tend to be usually much shorter than the one obtained from the marginalized fit. So the effect, as I was saying, the effect of next leading order correction on the fit is much smaller on single fit than on marginalized fit. Also, correction on single fits tend to be around 5 to 10%, while the one on marginal fits tend to be 10 to 30%. You can also notice that the only one that is a little different is the coefficient phi u, where the two of them are very similar. That's the coefficient that corrects the top. So what seems to happen is that the uncertainty there actually start spreading through over the fit rather than staying only in the part where you're interested in. So it starts spreading everywhere. Now, even more interesting, at least for me, is looking at future collider. Oh, sorry, I didn't write that, but these are again results from marginalized fit for LEP, ILC, and FCCE, leading and next leading order. And what you can see is that in all of these cases, or yes, in most of the operators, the FCC seems to have exactly the same result of LEP, at least in terms of modification induced by next leading order correction. So even if you obtain much more precise, much better bounds on all your observables, because of course you have more powerful machine and you have better, much well measured observables, the size of the next leading order correction are the same. And this is even more clear in this other plot. Well, you can see that clearly there is no difference in the size of these next leading order corrections when talking about FCC or LEP, while instead they tend to be very small for the ILC. This is maybe due to the fact that ILC is very good at putting constraint on the phi u coefficient due to the fact that it gets most of its constraint from polarized beam, from asymmetries. And ILC has more polarized beam, so it's much better in that regard. So what does all this mean? What does all this mean? Well, in general, one would expect to have very small next leading order corrections. In particular, if you consider that for the majority, there are electroweak corrections. Instead, what you obtain is that the fit to the subnormal lift can actually get correction of order 20 to 30%. So they are very relevant to the fit. Something that it's at least for me even a little bit more interesting is that it looks like the size and the sign of this correction does not depend measure the quantities, how precise you can measure your Sorry. It says your internet connection is unstable. Can you still hear me? Hello?
Yes, I can hear you.
Okay.
There was a small glitch, but it's okay now.
Okay, because it says, sorry. So where was it? Yes. So it seems that it depends more on how you're doing the fit and or how you're doing the measurement rather than how precisely you're doing your measurement. So that means that these studies, this next leading order correction, should be incorporated at least in more general fits, apart from the fact that it can be used, as I told you before, to try to correlate different observables, but different, measurements. It's also, they seem to be actually important to keep under control the uncertainties in your fit. Now, final thoughts. I think I'm perfectly in time. So final thoughts. The standard model is, the standard model FT is a very good theory, but unfortunately it has a series of illnesses. And what makes it most attractive for us, the fact that it can be used for a general model independent description of new physics, makes it also very difficult to use because we have a huge amount of operators. Not all of them can be easily bound, and you are, well, sorry for the play of word, but you're bound to have flat directions and so on. So that makes it complicated. Also, it appears that they are very sensitive to next reading order corrections. So I would say that probably that means that are also very sensitive to, in general, to uncertainties in your theory and your experiment. So that's something that has to be worked out much better in all these fits. So it's something that it has to be worked out correctly. Otherwise, the fit becomes meaningless. There are other problems in the Southern model, that in Southern model FT that I didn't have time to talk about, but let me just give you a brief idea. So one, I said before, is the fact that the Southern model FT assumes that the Higgs is an SU2 doublet. However, you have other EFT like the HEFT that treats it as a pseudo-Goldstone boson of some higher symmetry, higher scale. And the problem here is that in general, the HEFT, well, the HEFT is more general than the standard model FT, of course. There are UV theories that cannot be studied in a standard model FT. Simple one. I mean, I'm not saying anything crazy like a singlet whose mass gets all its mass from the electroweak breaking. It cannot be represented correctly in the standard model FT. It has to be represented in a HEFT. So HFT seems the best option, but then there you have even more problem regarding huge amount of operators and not having everything under control. So that makes it even more complicated. There is a second one that also is a little tricky. That is the debate over keeping or not a 1 over lambda fourth terms. So I already told you that at amplitude level, one keeps only 1 over lambda square, meaning dimension 6 terms, and throws away everything of higher power of lambdas. However, when you square the amplitude, if you don't keep lambda to fourth terms, you would obtain cross sections that are not positive definite. So so that's a problem for the experiment, or at least for the theory. But then it becomes a little difficult to understand why you should keep those terms and not the one that simply comes from interference with dimension 8 operators. So this is something that is still in debate. So just not to leave you on a downer ending, indirect searches cannot provide us with a map towards discovering physics, but maybe they can give us a compass. The EFT can help us make good use of the indirect, the information that one can obtain from indirect searches and precision physics. However, the effective field theories, the standard model EFT has still a lot of problem, let's say, a lot of things that will have to be worked out. The good news is that there is a vast community of people working on these topics, ranging from experimentalists to theoreticians in many different directions. Not all of them agree on what are the issues that have to be solved and how to solve those issues, but that's for another time. But at least it's a good news that this instrument is being refined all over. So, well, thank you for your attention, and I'm finishing.
Thanks a lot for this very interesting and comprehensive talk. If there are questions, please raise your hand. Maria Jose is already muted. Okay, you talk first without raising your hand. Go ahead.
Should I? I don't know how to do it. Sorry. All right. May I?
Yes, go ahead.
Yes. All right. I have two very short comments and one question.
Yes.
The first comment is regarding the comparison between the SMEFT and the IGFAE.
Mm-hmm.
When I was thinking about this, I found one very peculiar thing regarding the potential. I mean, the self-interactions in the Higgs sector, which
Mm-hmm.
makes a very peculiar issue regarding the correlations you were mentioning at some point. In other words, if you compare the trilinear and the quartic Higgs coupling,
Mm-hmm.
there is a very, very different behavior in one effective field theory versus the other, because in the
Mm-hmm.
SMEFT, as in the standard model, as you said, the Higgs is within a doublet, it's inside the doublet, and therefore immediately there are correlations that you get when you go to the physical field, the Higgs, you find
Mm-hmm.
a correlation between H³ and H4. However, in both, in the SMEFT and in the standard model. However, in the HEFT, you don't find such a correlation because the Higgs is a singlet. So in that regard, there is a huge difference. So with phenomenological interesting consequences. This is one comment.
Absolutely. And if I can add just
Sure.
one thing, absolutely. And I would also add that this is true also for other couplings, like, for example, Higgs to 2 vector boson.
Yes,
the coupling with
exactly.
2 Higgs into vector boson. Yes, exactly. And
we are, in fact, we are working on that also. Not only,
oh,
I mean,
okay.
not in the SMEFT, but in the other approach. But anyway, it was just a comment which I find interesting.
Yes,
the
absolutely.
other one is regarding the comment I already told about the gate choice.
Mm-hmm.
The gate choice, it is relevant when you do the computation, in the sense that you are doing, as you were mentioning, for instance, a 2-loop computations of electrowave precision observables. Of course, the observable does not depend on the gate choice, but in fact, for the technical computation, you have to choose one gate. I mean, when you perform the computations to 2 loops, you have to you have to fix the propagators of the W's and the Goldstone bosons and so on. So you have to make a choice of the gauge, and at the end, presumably, you are getting a gauge invariant quantity prediction.
Yes, I agree. Sorry, may misunderstood your question before. Yes, absolutely. Simply that in our case, we work in arc-C gauge. So
this was precisely my question.
Yes, thank you. I misunderstood the question. Yes, we work in arc-C gauge, and then we verify the XC.
All right. So when you are talking in the last part of your talk of next to leading order corrections, you are doing a lot of computation of diagrams and so on and so forth. And I am assuming that you are doing that in the arc gauge. Of course, the final result is gauge independent, but this is the power of not using the kappa formalism. If you use the full effective field theory, you are really doing the explicit computation and checking, presumably, that you are getting gauge. I guess this is what you are doing.
Absolutely, yes.
Gauge.
Yes.
Okay.
Yes.
Very good. And the third point is more a question than a comment, is regarding the effect of the lambda choice. In other words, you are doing a fit and you are discussing of singular versus marginalized fits, but you never mentioned that you are fixing, you are setting to a particular value of the lambda. My question is...
I said, sorry, I said
wait,
at the beginning, but yes, sure. Go ahead.
My question is, how would be the interpretation of your fits if you also include the lambda as a parameter and you fit the whole thing, including lambda? As a free parameter.
Okay. So we set the lambda at a scale. Of course, we set lambda 1 TV. Well, usually what happens is that if you leave lambda free, you can... Okay, one thing you can do is simply redefine these coefficients. For example, the one given here, instead of defining as C, you're defining as C over lambda.
No, but imagine I choose, instead of lambda, I choose, instead of lambda equal to 1, I choose 3 TeV.
Yes, that simply would...
is my fit or my conclusion you are extracting that the next two leading order corrections are relevant or not to 20 to 30% change? I guess yes.
No, I would say no, because if you change the scale lambda, what happens is that what happens is that all the coefficients are rescaled by a factor, and so this object that they define here, the factor on which the scale cancel between the two in the ratio. So this plot would be the same, would stay the same.
I'm not so sure because you are renormalizing. You are doing
Maria Jose is 1 over, he's redefining is C over lambda squared.
No, it's not only that, because the lambda is also involved itself in the computation of loops and so on and so forth. So
lambda is not renormalized. Lambda.
I know. Lambda is like, if you want, you may interpret lambda also as the renormalization scale. Not only the lambda that is trivial in front of the coefficient, but you also have a scale going around.
Okay. This is okay. Maybe I can answer you better. Okay. So you can do that. However, that makes a little bit more well, okay, let's say what we did actually is that we set the scale of the coefficient at the electroweak scale. So all these coefficients that are presenting here, this number that I give you here, are defined at the electroweak scale. So the
amigo, yes,
is the electroweak scale. So we separate the scale of the running and the scale of new physics. If you incorporate that in the running, then it's different. Then I agree with you, that would be different. However, the problem is that in order to do that in a completely, in order to make sense for this kind of computation, you need to have the RGs at 2 loop for the coefficient, because since we are doing the calculation of these objects at next leading order, we need all the next leading order RG. So we need 2 loop object RG in order to do the RG scaling of this coefficient.
I understand your point, and I stop already. But from my point of view, the most intuitive choice would be the same scale for both. If you are doing a fit to data that is also running at 1 TeV, like LHC data and so on. So the obvious thing is to identify somehow both scales. The one that you put in the coefficients in the running, and the one that you put just to adjust the dimension of the operator to 4, to the Lagrangian dimension 4, in the denominator lambda squared, lambda cube, etc.
So I agree with you, but I disagree with you. I agree with you that should be at the level of the scale, but these are all of these are electroweak observable, so they are defined at the pole of the Z. So it actually makes more sense to define the coefficient at the pole of the Z. So that's why so that's a very interesting point, and we try to work it out in the best way. What we found out at the end is that it made more sense, also from a mathematical point of view and from a theoretical point of view, to simply define the coefficients at the electroweak scale. So all these coefficients are the MZ scale, basically, at the mass of the Z. They are defined at the mass of the Z. Because initially we wanted to run it at a scale lambda, but we couldn't run it without being inconsistent with the kind of calculation we did.
Okay. Thank you very much.
Try to separate, but yes, of course, you can put them all together and would be.
Okay, thanks, Paolo.
Thank you.
Very good. Are there more questions? Well, let me ask a question. You evaluate the sensitivity to your coefficients here by looking at the electroweak observables. Yeah. Of course, I mean, there are also other observables that where these enter, correct? Yeah, as I understand.
So these coefficients, yes, absolutely.
And
Sure.
I mean, are they taken? They are not taken into account in your fit because you think that the electroweak precision observables will give you the best access to them, yeah, and the others do not play a relevant role.
So the answer is double, actually. There are two points to this. The first point is that exactly what you're saying. The majority of these operators enter predominantly in the electroweak sector, and they don't really, you don't really get much information from other sectors, for example, from the Higgs sector. So there is at least, sorry.
You showed also the diagram with the correlations, for example.
Yes, exactly. You get all the correlation, but right now, those are also for future experiments, etc. But right now, considering Higgs data, lab data, etc., LHC data and lab data, for the most part, the lab dominates for this. You get some term, you get a little bit of, you can get a little bit of, I would say, you can get a little bit better in constraining this using Higgs data, but it doesn't really help too much. Apart from the coefficient C5WB, the second one in the list, that also enters quite predominantly in Higgs data, that actually would get much better getting Higgs data. However, and this is the second and more important point, is that in order to do this analysis complete, we would need the complete calculation of next reading order correction to Higgs data. Now, there are mostly of the decay of the Higgs are done, at least, well, all the decay of the Higgs are done. Although not completely. For example, there are a result of the decay of the Higgs into Z's instead of Higgs into Z plus virtual Z. So it's not exactly, they're not exactly perfect, but there's something. However, there's really nothing complete for the production of the Higgs. So at the very end, the problem is that we don't have enough theory behind to do that. That would be next step, maybe. I mean, if this takes hold and people start using and seems reasonable, maybe it would be reasonable to add it.
And maybe one little follow-up concerning the triple Higgs coupling. You are mentioning that this can be done indirectly via the Higgs data, but also indirectly via the electroweak precision observables.
Yes.
Can you remind me what is the precision that we have right now for this? Or yeah, exactly, the two lower.
Yes, the two loop. Sorry, what precision? What do you mean?
I mean, there is already a precision that one gets from current data, or maybe from expectations from future colliders on the triple Higgs coupling.
From electroweak precision observables?
From both, from the Higgs data via the EFT and from the electroweak precision observables via the EFT.
So I've here the result for the single Higgs. So right now the single Higgs at 80 inverse femtobarn is given there. You see it?
Yes, yes,
Okay,
but
so that's for the single Higgs. For the electroweak, I don't have it now. It's pretty large in this moment, so it's not using round one data. Yeah.
You were cut off. You were cut off for a moment. Can you explain again about the electric precision?
So yes, electric precision data. So I didn't give you the constraint here. What I can tell you that are not very different from the one that are given when combined with single Higgs. So more or less are those one. 4 years ago of data. 4 years ago of data. Those are the constraints that you obtain. And in the paper we are working out, we are actually redoing it using new data, new electroweak precision observable, etc. And they're slightly better, but for now it's still preliminary, so I'm not going to give you an answer of what's happening now, because I don't want to give you an answer that is wrong, mostly because we're still studying it, so it's nothing.
Sorry, what you call single Higgs is the production of a Higgs together with a Z or something else, I guess, no?
When I say single Higgs processes are processes where you have n Higgs and maybe something else, so it could be.
So it's not gluon. It's not gluon giving just one Higgs, isn't it?
Could be, yes. It's also
no, because kappa lambda is not involved.
It's involved at 2 loops.
Ah.
Yes, that included too. So yes, it's included in the 2 loops. Like for example, also the decay of the Higgs into photons is it's included because it's 2 loop object. It's still a next reading order. So
okay, if you are referring to 2 loops, I agree. Okay.
Yes, it's all next reading order. That means 2 loop for those.
Okay, thanks a lot. Any other pressing question? Doesn't seem to be the case. Then, Pier Paolo, thanks again that this worked out today. And
yes.
I'm looking forward to the new results that you were mentioning.
Yeah, hopefully it will come out soon. And will be good. I hope.
Forward to it.
Anyway, thank you very much for the invitation again. And it's been nice to see you, well, even remotely again.
Or in 3D at some point.
Yes, in 3D when all of this craziness will calm down.
Okay.
Okay, very good. So thank you again.